box beam? Yes or no? It's a combination of both. Okay, that's why. So with this example, you are able to see how to apply this in either a box beam or white flange. Okay, any questions, please? Anyone? No? Okay, good. Guess what? The next problem, I'm going to throw a big monkey wrench into your weekend. Okay, I'm going to make it worse. Okay, let's make it worse. Listen, this is one of the most complicated question that you can get. Okay, you cannot find any question more complicated than this. Okay, so I'm going to do example number 2 now. Example number 2. Okay, we're going to do example number. As I said, this is like seriously. Okay, when I started teaching this course 3 years ago, I had problem with this question also. But after putting the rules, okay, I can solve any questions on shear flow. And I want you to be the same. Okay, I want you to be the same like me at a younger age. Okay, I'm 50 this year, and you guys are barely 20. Okay, you guys are barely 20. Am I right or I'm wrong? Might be wrong. Okay, this is the example. Hold on, not this one. Come on. Hold on, I'm trying to get the example here. Okay, I'm trying to get an example here. Where is it? Where is it? Okay, I'm going to see. Hold on. Okay, you guys must be saying I'm a sadist. Okay, so this is the example we are going to look at. Okay, so this is the structure. Okay, so this example, what it wants us to find, that the structure is under vertical applied force. Okay, so knowing that tau max, same thing. Okay, tau max is equal to 75 times 10 to the power 6 Pascal. Okay, find the stresses at point A, B, and C. So that's what we have to do now. Okay, can someone tell me why this problem is kind of difficult? Anyone? What can you see? Can I go up for a second? Anyone? What can you see from this example?
Is it both thick and thin wall?
Yeah. So this example is both. We have to apply both thick and thin wall analysis. Yes or no? Right? We have to apply both. You have no choice, right? You have no choice. You have to. So we have a vertical force going down here, V. Okay, and I'm going to draw a transformation. Okay, I'm going to introduce your transformation now. So this is Y, and this is Z. We have a force applied at Vy now. Okay, so that is our applied force. Okay, so now this one you don't need. So it's based on it. So at point B and point C are what? Thin wall analysis. Question for you guys. Box beam or wide flange? Anyone? Box beam or wide flange?
Is it both again?
No. It's wide flange. Right? Okay, it's wide flange because if you apply a shear force here, or you apply a force there, you have one force going one side, one shear flow going the other side. Now you have how many start points? Start point number 1, start point number what? 2. Can you see that? You have 2 different start points. The left will not affect the right, so we classify it as what? Wide flange. Okay, then the shear flow comes over here, okay. So now once it is so at point A, it is a thick wall analysis. So when it's a thick wall analysis, you don't need to design your what? Your shear flow, right? So once it goes back into a thin wall, it goes like this. Okay, once it goes into a thin wall analysis, okay. I will see, can we finish this analysis in the next like 10 minutes, okay? So here we go, okay? So let's look at the shear stress at point C, okay? Let's look at the shear stress at point C. Now we know that the centroid is exactly at the center, yes or no? So I'm going to draw our centroid. Okay. So there is our centroid. Is exactly okay. That is our centroid. Okay. So let's look at, so the shear stress at point C, we are going to do thin wall analysis, and it's going to be based on wide flange, and we are going just 1Q, right? If it's box beam, it's what? 2Q. Okay. So we are just going to consider this area down here that I've drawn in dark. Okay. So again, Q at point C is equal to width, depth, y bar. So the width will be equal to 30. The depth is 10. Then that will be equal to 160 divided by 2 minus by 10 divided by 2. Okay. So this will be equal to 30 times 10 times by 80 minus by 5. So it's equal to 22500. Okay, so 22,500 or 22.5 times 10 to the power minus times 10 to the power 3 millimeter cube, or 22.5 times 10 to the power minus 6 meter cube. So now you see why it is important to lift things to the power of 3 to the power of 6. I don't need to press the calculator. It's just direct conversion. Okay. So from here, we can find the shear stress. Okay, we can find the shear stress. I'm going to write left and right. The shear stress at point C is equal to V over I. This will be the Q. And the thickness one, can someone tell me what's the thickness? Anyone? What's the thickness?
10.
Thank you. 0.01. Okay, so 22, because it's thin wall analysis, yes or no? Okay, divided by 0.01. So it's equal to 2.25 times 10 to the power minus 3. I better write properly. I should not rush. Okay. Okay. So for this case, I think a good practice, okay, that I think I should encourage you to do. you should put the thickness down here is equal to 0. What? 0.01 meters. Okay, I think this is good practice. Okay, so now let's look at, I'm going to use the same diagram. Okay, so you all can see better. Now we are going to find the shear stress at point B now. Okay, so we're going to find the shear stress at point B. Okay, so we're going to look for the shear stress at point B. So for this case, it's also under thin wall analysis. Okay, wide flange. You only have a single Q, and then we know that your thickness is equal to what? 0.02 meters. Right? So because it's coming here, it's going down this way. This is the thickness. Okay. So from here, you find your again your shear or your first moment of area at point B, right? So this will be equal to the first moment of area of point C. So this is 22.5 times 10 to the power 3 plus by the width is equal to 20. The depth is equal to 50. Excuse me. And then the y bar is 80 or 160 divided by 2 minus by 50 divided by 2. Okay, so this will be equal to, so this is 22.5 times 10 to the power 3 plus by 80 minus by 25 times 50 times 20. So this is 55 times 10 to the power 3. So this is equal to 22.5 power 3 plus by 55 power 3 is equal to 77.5 times 10 to the power 3 millimeter cube, or for this case is 77.5 times 10 to the power minus 6 meter cube. Okay, 77.5 times. So you can now immediately find the shear stress at point B is equal to V over I multiplied by 77.5 times 10 to the power minus 6 divided by 0.02, right? So this is equal to 77.5 power minus 6 divided by 0.02. So this is equal to 3.875 times 10 to the power minus 3 V over I. So now we're going to find the centroid. Now, I know if it's thick wall analysis, the maximum shear is always going to be at the what? Centroid. But for this case, you have a combination of thick wall and what? Thin wall, right? So for this case, the centroid might not have the highest shearing stress. We have to check. Okay, we have to check. Okay. So the shear stress at point A. So now we apply thick wall analysis. Right? And now the thickness is equal to 0.12 meters. Right? It is so big now. But also you have to consider we have more first moment of area. Right? You have much more first moment of area. So Q at point A is going to be twice the Q first moment of area of B. Yes or no? Right? So you have to consider both the left-hand side and the right-hand side now. Then plus the width is 120, the depth is 30, and the y bar is 30 divided by 2. Okay, so twice multiplied by 77.5 times 10 to the power 3 plus by 120 times 30 times 30 divided by 2. So it's 54 times 10 to the power 3. 77.5 power 3 times 2 plus by 54 power 3. So I get 209 times 10 to the power 3 millimeter cube. Okay, give me like 2 more minutes, okay? So this is 209 times 10 to the power minus 6 meter cube.
Can
Okay.
you scroll down a little bit, please?
I do apologize.
It's all right.
Because
It's all right. Thanks.
yeah, I'm on 2 screen, okay? So now, something happened to the words. It is always happen, you know. Microsoft is really okay. We're okay now. Okay, hold on. Let me put in such a way that you all can see. Okay, right. Oi, something happened where tau max is. Something moved again. Cheeky shot. It's okay. I'll fix later. So now, oi, wait. I'm finding point A. Okay, so the shear stress at point A is equal to V over I. No doubt we have a very big what? First moment of area, right? But we have to divide a very big width also, wide width, okay? So 209 power minus 6 divided by 0.12. So this will be equal to 1.74 2 times 10 to the power minus 3 V over I. So now you realize that, hey, the centroid is not biggest or highest, sorry, the maximum shear is not necessary at the centroid now. When you have a mix of thin wall and what? Thin wall, yes or no? So from here, we know that, so if you look at the 3 values, yeah, look at, I'm almost done, guys. I'm okay. You look at 3 values, so you can make this conclusion that tau max will occur at where? Anyone? Tau max will occur at point where? At point B, right? So now you say that tau shear stress at point B will be equal to 3.875 times 10 to the power 3 minus 3 V over I, and this thing will be equal to 75 times 10 to the power 6. So from here, you know your V over I ratio is 75 power 6 divided by 3.875 power minus 3. So this will be equal to 19.35 355 times 10 to the power 9 Newton per meter 4. Okay, so from here, you can immediately find out your shear stress at point C. So therefore, it's just a matter of substitution now. You guys will know that. So because V and I, why we can use this number? Because V and I, rule number 1 is V over I is constant for everywhere, yes or no? So 3.55 times 10 to the power 9. At point C is what? Point C is 2.25 times 10 to the power minus 3.
Professor,
Right?
I think you made a typo. You wrote down T max will occur at B, but I think you meant to put C.
No, it's at B.
Oh, then how come on the bottom left it says point C is where T
Oh,
max
this one
occur?
because something happened. This one something happened. It's a Microsoft thing. Okay.
Okay.
Okay. It shifted. Okay. That's why I'm so annoyed with Microsoft.
Oh, I see. I see.
Yeah. Do you have the same problem like me or no?
No,
Sometimes
I don't use OneNote.
Oh, okay. So 2.25 power minus 3. So this is equal to 4. 4. I got something wrong. It's 2.25 power minus 3 times by 19.355 power 9. So it's equal to 43.55549 megapascal. And therefore, the shear stress at point A is equal to 19.355. Today, my handwriting look like shit. Sorry, it looks really bad. 42 times 10 to the power minus 3. So this is good 19.355 power 9 times 1.742 power minus 3. So this is equal to 33.716 megapascal. Okay. End of lecture. Okay. So what you'll realize is thin wall analysis is not that difficult, is it? Yes. Okay. and we just add on to our rules, yes or no? Okay, we just add on the rules. If that's the case, I'm going to end this lecture. Anyone have any question, I will still be around to answer any of your question. If not, you know what, have a fantastic have a fantastic, what do you call, have a fantastic weekend. Okay.